Hey, welcome back. All right, so I had a couple of requests to maybe explain a couple of questions on a previous quiz that we just took. I've got the problems here on the screen, so let me go ahead and put them. I'm going to begin with question number 9. So if you're taking the course, obviously this is going to be a previous question on quiz 4 and also quiz 10 that's in the background. So I'm going to make quiz 10 question a little bit smaller. Only so that I can bring up the information here on the front for question number 9, and then when we're done we'll move on to the next problem. And so what you can see here is that this question involves the use of stoichiometry. Now there are two options that you can use. You can use the grid method that I've shown you in previous videos that kind of go quickly on how to solve the problem, or you can use the long method, which is known as the regular stoichiometry. I'm going to go ahead and use the stoichiometry method here in this problem, just so that we can show you how to do it, because remember on the AP exam it's the stoichiometry that's going to be looked at as the method of preferred choice for full credit on free response problems. All right, so what we've got is we got a stoichiometry problem. The problem is identified here. It gives you a reaction that we need to deal with. It's already balanced. We know that already because it kind of tells you so. In the problem, this is a problem that was used in a previous question on the quiz, but you're asked to consider the following chemical reaction. You need to assume that you ran the experiment yourself and that you reacted 36.3 grams of the oxygen, which is this reactant here, and 15.6 grams of C2H3Cl for this second compound here. Okay, so if you're setting this up on the grid, you want to set that up there, but remember I said I was going to use the stoichiometry, so let me go ahead and use that. I'm going to just make this a little bit smaller, give me a little bit more real estate down below, and begin with the work. And so I'm going to use stoichiometry, and I'm going to begin with, I'm just going to use the first mass that's provided here. So they give me the first mass, and that's going to be the oxygen. So I'm going to say here, we've got 36.3 grams of oxygen, and what I need to do is convert this to moles, because I really want to know how many moles of the oxygen do I really have that corresponds to this 36.3. So in order to do that, you want to go ahead and use the stoichiometry here, and because we have grams as the starting amount here in the numerator, the next step is going to be the conversion factor of the molar mass, which is a grams to mole ratio. For every 1 mole of oxygen or any other substance, it has a very specific mass. In this case, oxygen is a mass of 15.999 for every oxygen atom. Let's go ahead and, for the purpose of this solution set, I'm going to use rounded numbers just so that we can give you a quick answer, but clearly on your end, you want to go ahead and use the actual precise mass for the oxygen. And don't round anything, okay? But I'm going to go and do that here only so I can get through the video quickly, just to give you the quick general guidance. So here we know that 1 mole of oxygen is going to have a mass of approximately 32 grams of oxygen, and this is going to give us a mass here. In the numerator, if you multiply across, you're going to wind up getting 36.3 grams, and so the grams here are going to cancel here and here, so that will give you moles of O2, and in the denominator you're going to have 32. So there are no, actually we need to make sure we get rid of this grams there. So the only units that will remain here are going to be the mole units. So if I take that 36.3, go ahead and divide that by 32, this is going to give you approximately 1.1343 moles of O2, and it's important here that we identify here this is going to be at the start. Okay, you want to go ahead and repeat the same process for the other compound, and so I'll put this other compound down here. We have 15.6 grams of C2H3Cl, and we got to figure out how many moles we have at the beginning. So we know that 1 mole of C2H3Cl is going to have a very specific mass. So grab your calculator and add along. The chlorine atom is 35.453. We add 3 hydrogen atoms. I'm going to add 3 to that mass there. And then we're going to add the mass of 2 carbons. So we're going to add 12 plus 12 giving us approximate mass here of 62.453 grams for C2H3Cl. And if I go ahead and do that, notice the grams of the compound cancels, leaving me the moles here. So what we're going to wind up getting over here is going to be 15.6 moles of the compound divided by the approximate 62.453, which if we follow the math out all the way here, 15.6 divided by that mass down below should give us a mass of approximately 0.2497. And this is going to be moles of the C2H3Cl. Okay. Now this amounts that you see here correspond only to the amount of moles that are present at the beginning for this particular reaction. And the question that's asked here is to identify the number of carbon monoxide that is produced. And remember, carbon monoxide is one of the products. So the first thing we need to do is identify which is the limiting reactant. Now, if you've already solved the problem before, you would already know this, but I don't have that luxury here to show you that, so I'm going to go through the entire workup, and you would have already had that done. But let's pretend that that information was not available, so you have to solve it here. Now, what do? You pick one or the other of the compounds at the start, so that means that you can either pick this amount here, or you can pick the other amount. It doesn't really matter, just pick one, and then we can compare the moles of the start that we have of a compound versus the moles that are needed for that compound, and then we can go from there. So the numbers that you use are going to depend on which compound you select. Since I started the first one up here, I'm just going to go ahead and select oxygen as the compound that I'm going to use. And so I'm saying that if I have 1.13 moles of oxygen, how many moles of the other compound do I need? And so in order to do that, I'll just continue the work here. In fact, what I'm going to do I'm going to kind of move this, make this a little bit smaller, just to give me a little bit more space. Do the same thing for the one down here. And then that'll allow us to do the work that we need to do here. And so if we do that, the ratio that I need to consider now is going to be the relationship between the oxygen and the others. So notice the ratio here between the oxygen is a 3 and the other compound is a 2. So the ratio is a 3:2 ratio. So that means that for the oxygen, I'm going to have down here in the denominator moles of oxygen, and in the numerator it's going to be moles of the C2H3Cl. And the ratio here is a ratio of 3 of the oxygen gas for every 2 moles of the C2H3Cl. And so doing this math out, go ahead and multiply across. You're going to take that 1.1343, you're going to multiply that times 2, and then you're going to divide it by 3, and that should give you the following number. And so that should give you here 0.7562. And this is going to be moles of C2H3Cl. But remember here, this amount here is the needed amount. Now, we already know how much we have at the start, and so we know that amount is down here. The only thing I did not write initially here was what was available at the start. So, in order for us to figure out how much we need, or whether there's excess or limiting reactant, we essentially take the amount that we have of the compound. So I'm going to take this one here, the start. So that'll be, I'm going to write this work at the top. So essentially we're going to say the amount that you have minus what you need will determine whether it's either positive or negative. If it's positive, it's excess. If it's a negative value, then there is your limiting reactant. So in this case, we've got 0.2497 that we have of that compound, C2H3Cl, minus the 0.7562. And so if you look at that, that number there is going to be a negative value. So what we know now is that this particular compound, I'm going to go and point an arrow to it, this compound down here is the limiting reactant. Okay? And so we're going to use this amount that I've circled here as the starting basis for how we determine the ratio of product produced. In this case, the product that we're looking for is the carbon monoxide. So let's go ahead and clear some work that we've got here. Let me move this information off of the page. And so let's take that out of the way, take this out of the way, that as well. And then that allows me then to move things a little bit up here. So I'm going to move this up. Don't want to do that. So what I want to do then is just kind of put this here, and I'm going to put it up here as a starting position. So that means I'm going to take the amount that I have at the start, which is 0.2497 moles of that original compound, C2H3Cl, and now I need to conduct the ratio between the two compounds, the limiting reactant and the carbon monoxide. The ratio that you see here, if you look at this, that's for every 2 moles of the limiting reactant, I'm going to produce 4 moles of carbon monoxide. Okay, so the ratio is a 4:2. So that means for every 2 moles of the C2H3Cl, I'm going to produce 4 moles of the carbon monoxide. Now the question is asking for moles, and so we don't have to convert anything else into grams. So this cancels, that cancels. And if you do the math here, you're going to have that 0.2497. That's very close when you multiply this by 2, because essentially 4 divided by 2 is 2. It's approximately 0.5. So 0.297 times 4 divided by the 2. And it's essentially here the answer, if you look at this here, is going to be 0.4994 moles of carbon monoxide produced. Okay, so you look for the answer choice that's closest to that, and that would be the answer choice you would put on the question. I think it's a multiple choice. Okay, and so that would be the answer there. And the last thing I want to mention here is it's for 3 Sig Figs. So remember, we need 3 Sig Figs. So if we do this here, the 4 counts, the 9 counts, the 9 counts. So the line is right there. The 4 is too low, so we're going to ignore that. And the answers that I accepted were 0.499, and I also accepted 0.500. So if you were within those regions there, then I actually gave the credit for that. So those are that's actually the solution for this particular problem. So what I'll do instead here, instead of making this a longer video, what I'm going to do is I'm going to make another video, and I'll just continue on here for question number 10. That'll be like a part 2. Okay, so if you haven't already done so, go ahead and subscribe. Keep watching, keep learning. We'll see you in the next one.